This next bit that we have to go through, this next road really, is a little bit of a tough road, but there's only one way to deal with it, and that's to get on it. So, atmospheric molecules have weight. Individually, they have weight, although individually one single atmospheric molecule is essentially insignificant in terms of its weight. I've told you, though, that the atmosphere can be detected 400 miles above us, and in reality, even further than that. But let's use 400 miles as the ceiling of the atmosphere, more or less. So if you take one single atmospheric molecule, it really doesn't amount to much of anything. But the combined weight of all of the atmospheric molecules that make up our atmosphere actually has some weight. It's like the laptop that I have in front of me. If I take my fingernail and I scratch that laptop and I scratch off one molecule and flick it into the air, it's nothing. But when you add up molecules and you put them together, eventually you get a laptop which has weight and mass and volume. The atmosphere acts in a very similar way, so that over those 400 miles, you do begin to accumulate some weight as a result of all of those atmospheric molecules that are making up the atmosphere. I'm going to use the swimming pool analogy or metaphor. When I was a kid, I would go to the park down the street from my house, and my friends and I would pay 25 cents, and we would go swim during the day during the summer. It was like 2-hour sessions. We'd go to one part of the pool where there were diving boards, and the swimming pool was 12 feet deep. We would jump off the diving board and we would race down to the bottom of the pool to try to touch the 12-foot, the bottom of the pool. I recall that as I would do that, I felt like my head was going to be smashed, because effectively what was happening as I swam deeper into the pool to reach down to touch the bottom of the 12-foot of the pool, I effectively had 12 one-foot buckets of water on my head. And all of that weight created pressure on my head. The atmosphere acts in a very similar way in that we are down here at the surface and there are hundreds of miles of atmosphere above us. Because we live down here, are born down here, reside down here, and exist down here, we don't notice that weight. But if we went up higher in the atmosphere, you begin to notice that there is indeed weight to the atmosphere. So, the force exerted by that weight of the atmosphere is called air pressure. Gravity pulls the atmosphere down towards the surface of the planet, and because of that, the atmosphere is very dense along the surface of the planet, kind of like a pancake, and then it thins out as you go further up. The atmosphere, just like water, is a fluid body. If I took a glass of water and I poured it onto a table, what gravity is going to do is flatten out that water on the table, because water is a fluid body. If I took a chair and tossed it on the table, the chair is a solid body. It's not going to flatten out because of gravity. Well, the atmosphere is a fluid body just like water is. So gravity pulls the atmosphere down along the surface and flattens it out along the surface, kind of like I said, like a pancake. This is a critically important component. Increasing altitude results in decreasing air pressure and decreasing air density. Air density is the number of atmospheric molecules per cubic unit. What that means is this. If you had a 1 by 1 foot cardboard box and it was empty and you were at sea level and you counted the number of atmospheric molecules in there, and then you brought that same box up to 10,000 feet and counted the atmospheric molecules there, and then up to 80,000 feet and counted it there. This is what we're talking about with air density. How many atmospheric molecules are there per cubic unit? It doesn't matter what kind of cubic unit you use as long as you compare like cubic units. So again, increasing altitude results in decreasing air pressure and decreasing air density. Take a look at these two pictures. These are the same bags of chili cheese Fritos. On the left-hand side, here's that bag at sea level, and on the right-hand side, this is that bag at 9,000 feet at Mammoth Lakes, California. Notice at sea level, the very weight of the atmosphere is compressing the bag of Fritos. Whereas at 9,000 feet, because the weight is significantly less, you are above a large percentage of the atmospheric molecules. The result is there's less force, less weight, and the air inside the bag is able to expand outwards. This is just a practical application of air pressure. Take a look at the diagram on the left-hand side. When you look at that, notice on the far left-hand side it says altitude in kilometers. 0, 100, 200, 300, 400, 500. Doesn't matter whether it's kilometers or miles. Then look down along the bottom, and you can see that it says increasing going to the right, which obviously implies decreasing going to the left. There are two things graphed on there. Air pressure in the purple line, air density in the orange line. Notice if you look carefully, both air pressure and air density decrease as you increase altitude. Notice how the lines as you leave the surface of the planet are going to the left, which would indicate decreasing. Then if you look just to the right of that, there's a 1 square inch column. If you notice, it says 1 square inch up at the top. And it says 14.7 pounds down at the bottom. Don't worry about that yet. All of those white dots are representing air molecules. Notice that there's lots of them close to the surface, whereas as you go up, there are fewer of them. This is what's happening with the air. As you go higher up into the atmosphere, the air gets thinner and thinner. Whereas down along the surface, because the atmosphere is a fluid body, gravity pulls it and compresses it down along the surface, like I said, like a pancake. Then if you look over the right-hand side, it's a very similar thing. The blue dots are representing air molecules. Notice it says air molecules are closely spaced at the bottom of the atmosphere, meaning the surface, and widely spaced at the top of the atmosphere. So that you can see down along the surface of the planet, you have a very dense atmosphere, whereas as you go higher, the atmosphere thins out. Let's take a look at some examples. At 18,000 feet, only 18,000 feet, which is just a little more than 3 miles, and remember, we're pretending like the atmosphere is something like 400 miles deep. At 18,000 feet, you're above half of all the molecules that make up the atmosphere, which means you're 50% of the way through the molecules, but you're only a small percentage, 1%, maybe even less than that, of the way up through the entire depth of the atmosphere, which means, once again, that the atmosphere is compressed down along the surface. Another good practical application of this is baseball at elevation. When baseball first moved to Denver, so when the Colorado Rockies got their team, there was a lot of question about whether that was a good place to have baseball. If you think about baseball, almost every team, with the exception of maybe St. Louis and Chicago, plays at or near sea level, where the air is denser. But Denver plays at 5,280 feet above sea level, a mile above sea level. And the result is this. When the ball comes off the bat, and it's routinely coming off at more than 100 miles an hour, no matter where you are, when it's struck and goes up into the air, and the ball's flying through the atmosphere in Denver, what ends up happening is this. The ball is just contacting quantitatively fewer atmospheric molecules, which puts less drag and less friction on the ball. And the result of that is that the ball flies farther, which means, of course, far more home runs. Now, someone might ask, well, what about the pitcher? Well, the pitcher only throws from 60 feet away. A ball might be struck 400 feet. And so the drag is going to be much greater on that 400 feet because of the distance that it's traveling, the number of atmospheric molecules that it's going to contact. And I don't know if you know this or not, but a curveball breaks less at higher elevation because there's less friction on the ball. You need friction on the ball with that spin to make the ball break. Again, take a look at these two diagrams, and you can see once again on the left-hand side, air density and air pressure are decreasing with increasing altitude, and you can see the 1 square inch column and all the air molecules down along the bottom. Now look at the one on the right. I drew a red line across it. Notice that below that red line, the air is very dense, whereas above the red line, it's much less dense. So imagine, once again, baseball in Denver. The ball gets hit, and as it gets hit, it's traveling through the atmosphere, and at a place like 5,280 feet above sea level, a mile above sea level like Denver is, the ball is going to contact fewer atmospheric molecules, and the result of that is going to be the ball is going to be able to travel farther. Back to the Frito bag. Take a look once again at the Frito bag. Notice this. Then on the left-hand side, now you can see what's going on. There are simply far more atmospheric molecules compressing that Frito bag when it's at sea level than there are at 9,000 feet. And the result of that is that the bag is able to expand at 9,000 feet.